It is red.
Take a look.
Oh, okay. Can I just do it with you, like with mine?
I mean, yeah. Why don't you go through it first, and then you'll have a chance to do it, just so you can really focus on what's going on. Okay, so let's go through our steps. What's the first step for related rates?
Identify snapshot.
Okay, good. And we'll want a picture here, right? Okay, so. A lot of times it's convenient to like embed these problems in the XY plane too. So how might we want to draw our right triangle here, do you suppose? I mean, this isn't the only way to do it, but it just seems like this would make sense.
You would just have
X and the Y might be the legs, okay? And then the hypotenuse would be, obvious then. So this would be one leg, that's another leg, and then there's the hypotenuse, right? It's an isosceles right triangle, so that's a right angle. Okay, so then what could the variables be? Okay, the length of, now the legs, there'd be a temptation to maybe call that X and Y, right? Do I want to do that?
No.
How come? They're the same, so it's only one variable. So let's just call it X and X, right? And then the length of the hypotenuse we could call whatever. We could call that H, or hypotenuse. How about it? Doesn't make any difference, right? Whatever you decide is fine. So there's our picture. Okay, we want to know at what rate is the area of the triangle changing when the legs are 3 meters long? We're going to answer, looks like several questions about this. So we can kind of use maybe the same template for all these questions. Okay. So then there are our variables. We want to write down snapshot values. So let's, if we can do part A, we can do part B, right? I mean, all that is just plugging in a different value for the legs. Oh, actually, no, it's not.
It's a hypotenuse.
Part B is the hypotenuse. Okay, so maybe they are different. Okay, so part A, what are our snapshot values? Okay, so for me, it would be X dot. Yeah. So we have X dot equals 6, and as long as we keep lengths in meters and times in seconds, we don't need the units on there. What else do we know for part A? X is 3. Okay, and what are we trying to find? Okay, so we're trying to find A dot, right? If A stands for area. Okay? Make sense? Okay, so what about, so there's our snapshot values. What's next? Parent equation. Okay, so what is our parent equation? Okay, 1/2 x squared is A. Good. So 1/2 x squared, 1/2 base times height. So area equals 1/2 x squared. There's our parent graph. What am I going to do? Differentiate with respect to time. So on the left side, I'm going to get A dot. Okay, the right side. What am I going to get on the right side? What do you think? Lana, what am I going to get on the right side?
X.
I'm going to get 2 times 1/2 is 1 times x to the 1, so it's just x. Okay, about that. So A dot equals x. And so then if I want to evaluate this, if I want to plug and chug, it's pretty simple. It's already solved for A dot. And so for the last step, A dot is just going to equal 3, right? Oh, sorry. Oh, sorry, x dot. Yeah, we forgot the x dot, didn't we? X dot. So it's going to be 3 times 6. Everybody see that? Because when we differentiate, we get 2 times 1/2. We get the derivative of hand squared is 2 hand to the 1, but then I gotta, by the chain rule, I'm differentiating with respect to t, so I have to do one more link in the chain, don't I? Right? Okay, so then we end up with our final answer is just 18, and what would our units be?
Meters.
Okay, meters squared per second. That's how fast we're accumulating area. Okay, so there's part A. Now what about part B? So what are we given this time? So we're still given, we have x dot, right? X dot equals 6, but this time they give us something bizarre. They're telling us that h is equal to 1, right? Okay, and they want us to find, just like before, we're trying to find a dot. Okay, so what do you think? I mean, we can still use the same parent equation that we had before, right? But what's the problem in part B?
We don't have it.
We don't have x, right? We don't have x, and so what are we gonna do? Suggestions, James, I'm sorry. But, okay, right, we could find x, couldn't we? So for our snapshot, if we took our snapshot situation when h is 1, we could just create a little right triangle. And for our snapshot, if that's 1, then we know by the Pythagorean theorem, x squared plus x squared equals h squared, right? So 2x squared equals h squared. So h must equal square root of 2x, right? So x equals h divided by the square root of 2, right? Okay, and so then we have a choice. We could solve this thing, like we could write area in terms of hypotenuse if we wanted to, and plug that value in, but wouldn't it be easier instead just to add another value to our snapshot list, right? Because at this frame in the video, when h is equal to 1, we can see that x equals 1 divided by the square root of 2, right? And if you want to rationalize that and make it square root of 2 over 2, that's fine. I just leave it like that. And so now we do the same calculus as before. When we differentiate implicitly, we're still just going to get a dot equals x dot, only now the value we're plugging in for x is 1 over the square root of 2. Okay? Make sense? So I guess the moral to the story there is we wanted to add this extra value to our snapshot list. Okay? Remember, and it's these are two different pictures that we drew, right? This picture up here that had the variables in it represents the changing triangle because we've got the x and the x and the h in there as variables. But this picture down here this is a snapshot, right? At that one frame of the video, those are the dimensions of the triangle, right? And we just want snapshot values that we're plugging in at that one frame. Okay? So we can populate this list with other stuff if we can calculate it. That's okay to do. We can kind of move backwards in the problem and add more stuff to the snapshot list. Okay? Does that help? Okay, what about the last part then? At what rate is the length of the hypotenuse changing? So I guess for part 3, we've got the same stuff we had before, right? And they don't even give us a specific value there, do they? Okay, so what does that probably imply about this? I mean, one of two things. Either our answer is going to have to include some variables in there that we're not given, right? Or maybe it's independent. Maybe it's a constant rate. and the hypotenuse increases at a constant rate that's independent of the side length of the triangle. Okay, we'll see. So for part C, we still know that x dot equals 6, and that's all we're given, and we're just trying to find h dot, right? Okay, so what's our parent function gonna be this time?
2x squared.
Okay, this is Pythagorean theorem, isn't it? Because the equation that relates x's and h's is not the area. We don't want to introduce some other variable in there that we don't need, right? So our parent function here in this case is going to be the Pythagorean theorem. So we get our 2x squared equals h squared, right? Okay, and if we differentiate, what's that going to give us? On the left side, if we differentiate with respect to t, we're going to get,
4x.
so the derivative, I get the 4 times x times x dot, right? Because I'm differentiating with respect to t, so I got 2 layers to that derivative. On the other side, I'm getting 2h dot, okay? And so the problem then is if we want to solve for h dot, well, you can see the issue here, right? I can divide each side by 2 and make that a 2, but I'm going to get h dot equals 2x x dot over h, right? Right? What's the problem? I don't have h and, I don't, well, I have x dot,
Or x.
but I don't have h or x, do I? Right? What can I do with my parent equation up here, though?
You can put it,
I mean, we kind of did that work above, right? If I square root both sides, and if I ignored the fact that there's a plus or minus there because h and x have to be positive, don't they? Right? They're lengths of a triangle, they're dimensions, so they couldn't be negative. So we get the same thing as before. We get h equals 2 times the square root of x. There's a secondary equation. That's useful to us, isn't it? If I plug that in for h, look what happens. Right, if I plug that in for h, I'm going to get 2x x dot over the square root of 2x. Aha. What happens?
the x.
You see that? The x's cancel algebraically. So that's the math god's way of saying it's independent of x, right? It's a constant. So h is just equal to 2 divided by the square root of 2, which is what? What's 2 divided by the square root of 2? Square root of 2. Times x dot, right? And we have x dot. If we know the rate at which the side length is increasing, it turns out the hypotenuse is just increasing at a rate that's the square root of 2 times as fast. Right? So when we plug and chug, h dot just equals the square root of 2 times 6, and what? So well, that's our answer. 6 square root of 2, and what would the units be?
It's just,
There it is. Okay. That's it. Okay. All right. Hopefully that gets you loose a little bit. So I'm going to let you continue to work, and I'm going to give